At the center of our galaxy, behind curtains of dust and crowded starlight, a few stars move as if they are circling something that refuses to show itself. They sweep around an invisible point at extraordinary speed. One of them curves so close to the center that its path becomes a kind of cosmic clue, a bright thread pulled tight around a darkness. There is no ordinary star there, no glowing surface, no object we can simply look at and name. Only the motion gives it away. Before we go deeper, take a quiet moment to settle in. Tell me where you are listening from tonight and what time it is there. Somewhere above you, beyond the light of your room, beyond Earth's atmosphere, beyond the moon and the slow drift of planets the universe contains, places where light itself reaches a boundary and cannot return. Black holes are often described as cosmic monsters, but that image is too loud for what they truly are. They do not need to chase anything. They do not need to announce themselves. A black hole can sit almost perfectly hidden while stars gas space-time, and even time itself reveal its presence by the way they bend around it. And the closer science comes, the stranger the mystery becomes. We have watched stars orbit an unseen mass at the heart of the Milky Way. We have captured the shadow of a black hole against a ring of burning matter. We have heard the faint tremor of black holes merging through ripples in space-time. We have built instruments wide as Earth listened with detectors more sensitive than any human sense, and followed equations into regions no telescope can enter. Still, the central question remains: what lies beyond the horizon of a black hole? What happens to matter, time, and information after the last signal is lost? And why does every discovery seem to bring us closer to the answer while making the deepest part of the mystery feel even more unreachable? Tonight, we will move slowly toward that boundary. We will begin with what can be measured, then follow the evidence inward from stars and shadows to horizons, singularities, quantum heat, and the first enormous black holes in the young universe. Not to force the darkness open, but to understand why it has become one of the most important mysteries in all of science. At the center of the Milky Way, the night is not empty. It only looks empty to ordinary sight. Vast clouds of dust lie between us and the crowded heart of the galaxy, hiding the center from visible light. For most of human history, no eye could look there and know that something extraordinary was waiting in the dark. But the stars around the center were already telling the story. Near Sagittarius, a star, a small group of stars, moves with astonishing speed. They do not drift gently through space. They swing around an unseen focus, tracing tight elliptical paths around something that gives off no ordinary light. One star, often called S2 or S0-2, rushes close to the center and then curves away again, as if the darkness itself has taken hold of its orbit. There is no bright object at the focus. No normal star can explain what the motion demands. No ordinary cluster of dim objects can easily remain so compact and massive for long enough to fit the evidence. Yet the orbit is clear. Something heavy is there. This is one of the quietest ways a black hole enters astronomy. It does not have to shine. It does not have to appear as a visible wound in the sky. It reveals itself through gravity, by making nearby things move in ways they could not move otherwise. A black hole is sometimes imagined as an empty hole cut through space, but that image can mislead. It is better to begin with gravity. A black hole is a region where mass has been compressed so intensely that space-time curves beyond the point of return. Around it, matter can still orbit. Gas can still heat. Stars can still pass. Light can still travel near it if it does not come too close. The black hole itself remains almost silent. So, the first mystery is not what we see directly. It is what we learn from the behavior of what remains visible. Astronomers do not simply point a telescope at darkness and declare a black hole. Darkness alone proves little. Space contains cold dust, faint stars, distant objects, dead remnants, and empty regions where almost nothing glows. A black hole must be found through its consequences. It must be weighed by the obedience of its surroundings. A star circles an unseen point. Gas heats before disappearing. Light bends along paths that would otherwise be impossible. Two compact objects merge and space-time rings across the universe. The hidden thing leaves a measurable trace. At the center of our galaxy, that trace took decades to follow. The galactic center lies about 26,000 light-years away, buried behind dust and crowded with stars. Astronomers had to observe in infrared wavelengths where the dust becomes less blinding. They had to return year after year, watching tiny shifts in position become arcs and arcs become orbits. There is a special patience in this kind of discovery. No single night gives the full answer. A star moves slightly, then it moves again. Years pass, and the motion begins to curve. The curve becomes a path. The path becomes a measurement. The measurement points toward an invisible mass concentrated in a very small region. Over time, the evidence became difficult to avoid. The stars near Sagittarius. A star behaved as if they were orbiting an object roughly 4 million times the mass of the Sun. That mass had to fit inside a space far smaller than the scale of ordinary star clusters. Explanations involving dense clusters of dark objects became strained. The simplest and strongest answer was a supermassive black hole. But notice the nature of the proof. The black hole did not present its face. It did not emit a beam of light saying what it was. It was revealed by a long choreography of stars, by the way bright points moved around a center that remained dark. The stars became needles on an invisible compass. This is different from how we know most familiar objects. The moon reflects sunlight. A tree scatters light from its leaves. A distant star sends its own radiation across space. Even a faint planet can betray itself by blocking light or reflecting it. Ordinary seeing depends on messages coming from the object. With a black hole, the defining message cannot return from within the horizon. Science must approach from outside. This gives black holes their unusual status. They are among the most strongly evidenced objects in modern astrophysics, yet the part that makes them truly black remains inaccessible. We can measure their mass. We can detect their effects. We can observe the matter around them. We can hear the gravitational waves from their mergers. But the region past the horizon does not send news back. Before we go to that boundary, it helps to remember how strange it is that black holes became real astronomical objects at all. In the early 20th century, Einstein's general relativity changed the meaning of gravity. Gravity was no longer simply an invisible pull across space. It became a feature of space-time itself. Matter and energy curve space-time and curved space-time guides the motion of matter and light. In that new geometry, extreme collapse became possible. Carl Schwarzschild found a solution to Einstein's equations, describing the gravitational field around a spherical mass. Within the mathematics was a radius with a remarkable meaning. If enough mass were compressed inside that radius, escape would require more than the speed of light. Since nothing can outrun light, the object would be hidden behind a boundary. No ordinary signal could cross outward. At first, this was not instantly accepted as a real thing nature would make. The mathematics was unsettling. Some wondered whether the strange boundary was only a peculiarity of coordinates or an artifact of an idealized solution. Others questioned whether real stars with pressure rotation magnetic fields and messy collapse would ever reach such an extreme state. Equations can reveal possibilities, but science must still ask whether the universe uses them. That question led through the physics of dying stars. A massive star spends its life in balance. Gravity pulls inward while pressure from nuclear fusion pushes outward. When the fuel runs out, that balance can fail. The outer layers may explode. The core collapses. If enough mass remains, no known pressure can stop the inward fall completely. In that story, a black hole is not a monster appearing from nowhere. It is gravity winning the last argument. The theoretical picture grew stronger through the work of many scientists studying stellar collapse and compact objects. Later, Roger Penrose showed that black hole formation was not merely a trick of perfect symmetry. Under broad conditions, general relativity seemed to lead naturally toward trapped regions and singularity formation. When collapse became extreme enough, the possibility had become serious. Black holes were no longer only strange marks in mathematics. They became predictions of a theory that had already transformed our understanding of gravity, light, and the shape of the universe. If general relativity was right, nature could create regions where space-time closes the route back out. Observation then had to decide how often the universe actually did it. Some of the earliest strong black hole candidates appeared in binary systems, where an unseen compact object pulled matter from a companion star. As gas spiraled inward, it heated to tremendous temperatures and emitted X-rays. The invisible object remained dark, but the surrounding matter became bright. The pattern repeated. The black hole hid. The region around it testified. This is one of the great paradoxes of black hole astronomy. An object from which light cannot escape can sit at the center of some of the brightest phenomena in the universe. Gas falling toward a black hole may form an accretion disk, a rotating structure heated by friction, compression, magnetism, and gravity. Before matter crosses the final boundary, it can glow with extraordinary intensity. A black hole is seen not because it shines, but because the universe burns as it approaches. Yet not every black hole has a bright disk. Some may drift quietly through space, nearly invisible, unless they pass near a star or lens the light of something behind them. Others may stay dim for long ages, then flare when gas or a star wanders close. Their presence is not always dramatic. Sometimes gravity waits without spectacle. This makes Sagittarius a star especially compelling. It is not a quasar blazing across the universe. It is relatively quiet compared with the most active galactic centers. It does not flood our sky with visible fury, yet it anchors the crowded heart of the Milky Way, holding millions of solar masses in a compact region close enough in cosmic terms for patient observation to reveal its influence. The stars around it are more than background. They are messengers. Their orbits tell us the mass. Their speeds tell us the compactness. Their repeated passages allow tests of gravity in an extreme environment. Each star becomes part of a long experiment performed not in a laboratory, but in the deep center of the galaxy. There is a quiet intimacy in that. We live in the same galaxy as this black hole. It is not a remote curiosity in some unrelated region of the cosmos. It belongs to the architecture of the Milky Way. The sun does not orbit it closely in the way those central stars do, but Sagittarius, a star, is part of our galactic home. To understand it is to understand something about our address in the universe. Still saying there is a black hole at the center of the Milky Way does not mean the mystery has been solved. It means the evidence outside the horizon has become extraordinarily strong. We know the weight because of the motion. We know the hidden presence because the visible world bends around it. Science often works this way at the edge of the unknown. It studies what cannot be reached by measuring what can. It lets motion reveal mass radiation, reveal heat waves, reveal collisions, and absence reveal presence. This is not a weakness. It is one of science's most patient strengths. The first revelation is simple, and it is profound. Black holes are not known first by what they show. They are known by what they make the universe do. From here, the next question becomes unavoidable. If the stars revealed an unseen mass, could human instruments ever move from inference to image? Could we see not the black hole's interior, but the outline of the darkness it creates? Could the place where light fails leave a visible mark? For a long time, that seemed almost impossible. The black hole at the center of our galaxy is small on the sky and hidden behind dust. The black hole in the galaxy M87 is vastly larger but far farther away. To image either one would require a telescope, unlike any ordinary telescope, an instrument not built as a single mirror, but assembled from many observatories spread across Earth. The next stage of the journey begins there, with a planet turned into an eye and a darkness deep enough to cast a shadow. For a long time, the phrase image of a black hole sounded almost impossible. A photograph depends on light. Light must leave an object reflect from it, or pass through a scene and reach a detector. But a black hole does not return light from beyond its horizon. It has no ordinary surface to photograph. Its defining feature is precisely that signals from inside do not come back. So the first image could not be an image of the interior. It had to be an image of light failing around it. When the Event Horizon Telescope collaboration released the image of the black hole in the galaxy M87 in 2019, the world saw a dark center surrounded by a blurred ring of light. The image looked simple, at first glance, almost like a small ember with its center missing. But scientifically, it was far stranger than an ordinary photograph. It was the image of a shadow shaped by gravity, not a shadow cast on a wall, not a shadow made by a solid object, blocking light in the usual way. This shadow was produced by the paths of photons near an event horizon. Some light curved around the black hole and escaped. Some came too close and was lost. Around the darkness, superheated matter and bent light formed a ring. The black hole itself stayed hidden, but its absence had become visible. Before that image appeared, however, the black hole had already lived for decades in the imagination of science as something both certain and unseen. The public moment in 2019 felt sudden, almost like a curtain being lifted. But behind it was a long accumulation of theory instrumentation and trust in indirect evidence. For years, astronomers had watched the galaxy M87 with many kinds of instruments. They knew it was not an ordinary galaxy. A huge jet extends from its center, a stream of energetic material launched across thousands of light years. Such a jet does not come from inside the event horizon, but from the violent region around a central engine. The galaxy seemed to be telling us that something immense and compact lived in its core. Still, there is a difference between believing the engine exists and seeing the shadow of the place where light is lost. That difference matters because black holes are not ordinary discoveries. A planet can be photographed. A star can be measured by its light. A nebula can be mapped by glowing gas. But a black hole is discovered by what disappears, by what curves, by what refuses to send anything back from the deepest region. The Event Horizon Telescope was not trying to photograph a surface. It was trying to gather the pattern left by the absence of returning light. In a sense, the image of M87 star was built from a paradox. To see the black hole, scientists had to look at everything that was not the black hole. They had to study the hot matter near it, the radio waves coming from the surrounding plasma, the way strong gravity shaped the signal. The black hole was the missing center around which the visible evidence arranged itself. That is why the image was so powerful, even though it was blurred. It did not give us a crisp sphere. It did not satisfy the ordinary desire for sharp edges. Instead, it showed something more faithful to reality, a luminous uncertainty surrounding a dark region whose size and shape matched the theory. It was not a portrait in the usual sense. It was a measurement made visible. The public saw a ring. The scientists saw decades of mathematics and instrumentation meeting the sky. There is something almost tender in that meeting. Human beings living on a small planet around an ordinary star turned mountain observatories and polar stations into a single instrument. They synchronized clocks, moved hard drives across continents, filtered atmospheric noise, and compared independent reconstructions, all to see a darkness that had crossed 55 million years to become a trace in radio data. The image was not only about M87, it was about the reach of attention, and because of that, the image changed the emotional meaning of black holes before they could feel like invisible predictions present in equations and inferred from motion. Afterward, the mind had something to return to the ring, the shadow, the dark center. Even if the image did not show the interior, it made the boundary of the unknown feel physically present. It gave mystery a silhouette. The galaxy M87 is about 55 million light-years away. At its center lies a supermassive black hole billions of times the mass of the Sun. Its mass is enormous, yet from Earth, its shadow is incredibly small, like trying to see something tiny across a distance, almost beyond ordinary imagination. No single telescope could do it. To resolve such a small feature, astronomers used a technique called very long baseline interferometry. Radio observatories across the world observed the same target recording signals with atomic clock precision. Later, those signals were combined so that the whole network acted like a telescope with a virtual diameter close to the size of Earth. The image was not made by one eye. It was gathered by a planet. That detail matters because the final picture can look almost too quiet for the effort behind it. A soft ring, a dark center, a blur. But behind that blur were years of coordination, remote observatories, calibration, weather timing, algorithms, hard drives full of data, independent imaging teams, and the difficult task of making sure the result was not an artifact of the method, some data could not simply be sent over the internet. They had to be physically transported from observatories, including remote sites where shipment depended on seasons and conditions. The famous ring appeared only after enormous practical work, as if the universe had given a whisper so faint that Earth itself had to lean in to hear it. The light from near M87 star had traveled for tens of millions of years before reaching us. When it arrived, we needed the whole planet to receive it. The shadow seen by the Event Horizon Telescope is larger than the event horizon itself. This is because gravity near the black hole bends light dramatically. Photons can orbit or curve around the black hole before escaping while others are captured. The dark central region marks the absence of light paths that return to us. In this way, the image is a map of possibility. It shows where light could still reach the wider universe and where it could not. It shows matter and radiation moving through a region where space-time is severely curved. The ring is not merely decorative. It is the visible edge of a much deeper physical limit. This was why the image mattered so much. Astronomers already had strong reasons to believe that a supermassive black hole lived in M87. Jet's galactic dynamics and high-energy observations had long pointed toward an enormous central engine. But the Event Horizon Telescope gave the black hole's environment a shape that matched the predictions of general relativity. The size of the shadow, the structure of the ring, and the brightness asymmetry all fit the picture of a massive spinning system surrounded by hot plasma. The image did not solve the black hole. It confirmed the silhouette. 3 years later, in 2022, the Event Horizon Telescope revealed another image, this time of Sagittarius, a star, the black hole at the center of our own galaxy. This one felt closer in a different way. M87 star belonged to a distant elliptical galaxy. Sagittarius, a star, belonged to the Milky Way, to the same galactic structure that holds our sun. For decades, stars had revealed its mass. Now the dark center had a shadow. Sagittarius. A star was easier in one sense and harder in another. It is far closer than M87 star, but much less massive. Because it is smaller, the gas near its horizon changes on much shorter timescales. During the observations, the source flickered and shifted, making it difficult to reconstruct a stable image. It was like trying to sketch a candle flame during a long exposure, except the flame was plasma, moving near a 4 million solar mass black hole. The final image looked familiar, a dark center, a ring of light. The resemblance to M87 star was part of the significance. Two very different black holes, one enormous and distant, the other smaller, and in our own galaxy showed the same basic shadow structure predicted by the theory. Different masses, different surroundings, different distances, a shared signature. Science grows stronger when patterns survive comparison. One image may be extraordinary. Two images from very different systems begin to show that black holes are not isolated oddities. They are a class of object with recognizable behavior. Still, these images also teach humility. Some viewers expected sharper pictures, perhaps something like a dark sphere against a clear star field. Instead, the images were blurred ring-like and reconstructed from difficult data. That blur is not a failure of imagination. It is part of the honesty of the measurement. The targets are tiny on the sky, the signals faint, the atmosphere troublesome, and the Earth-sized telescope incomplete because we cannot cover the whole planet with observatories. The image shows what can be reached, and also what cannot yet be made clean. There is beauty in that, not the beauty of a perfect photograph, but the beauty of a limit approached carefully. The ring does not pretend the black hole is easy to see. It shows that there is just enough light near the darkness for human instruments to gather a trace. The shadow is therefore more than a picture. It is structured absence. Imagine light near a black hole as a vast field of possible paths. Some photons escape to space. Some are bent into arcs. Some loop around the black hole before breaking free. Others fall inward and never return. The shadow appears because the black hole removes certain paths from the sky. The darkness is not a painted circle. It is the missing light from paths that did not survive. This is central to the meaning of a black hole. Its darkness is not like a room with a lamp turned off. It is causal darkness created because events beyond a boundary cannot send signals outward. The shadow is the visible sign of that deeper silence. The Event Horizon Telescope did not look through the horizon. It did not defeat the limit. It showed the limit's effect on the surrounding light. That is why the image gave the human imagination a new anchor. Before, EHT black holes were strongly supported by stellar orbits, X-ray binaries, jets, accretion disks, and gravitational dynamics. But after the images, the invisible had a form people could look at. There is light, there is darkness, and the darkness has a shape. The ring around M87 star also carried motion inside its stillness. One side appeared brighter, partly because material near the black hole was moving at extreme speeds. Light from gas moving toward us can be boosted, while light from gas moving away can appear dimmer. The image may look frozen, but it contains the trace of enormous speed. The ring is a glimpse of weather near the edge. Matter near a black hole can orbit at relativistic speeds. Gas heats, compresses, and becomes plasma. Magnetic fields twist through it. In some systems, jets shoot outward over enormous distances. These jets do not emerge from inside the horizon. They are powered by the violent environment outside, where gravity, rotation, plasma, and magnetic fields interact. The black hole stays dark. The surroundings become luminous. That contrast is part of why black holes are so compelling. They are centers of silence, surrounded by testimony. Their interior gives us no light, while nearby matter can outshine galaxies. The shadow does not show the answer. It sharpens the question. What kind of boundary can create such a mark without being seen itself? This is the next step. The stars at the galactic center told us there was an invisible mass. The shadow gave that mass a visible outline. But the shadow is still outside the deepest mystery. To understand why the darkness cannot be crossed and reported from, we have to approach the event horizon. At first, we may be tempted to imagine it as a surface, like the surface of a planet, or a wall, or the rim of a well. But the true horizon is stranger. It has no material texture. It does not glow by itself. A hand could not feel it as a physical shell. It is a boundary in the possible paths of light, matter, and cause. The image from EHT gives us courage to move toward it, but it does not make it ordinary. So we leave the glowing ring for a moment. We move from what the telescope can see to what no hand can touch. And there, the black hole becomes less like an object and more like a change in the future. The shadow gives the mind something to hold a dark center, a ring of light, a visible trace of something hidden. But the event horizon itself is not that ring. It is not the orange glow. It is not the blurred edge in the image. The ring belongs to matter and light outside the final boundary. The horizon is deeper, quieter, and more difficult to imagine. It is the point after which no signal can return. The name sounds almost familiar. A horizon in everyday life is the far line where sea or land seems to meet the sky. It looks like an edge, though we know it is only the limit of our view. Travel toward it, and it moves away. It does not stop you. It does not have a physical surface. The event horizon borrows that word, but changes it completely. It is not simply the limit of sight from where we stand. It is a boundary in causality. Events outside it may still send light outward. Events inside it cannot. A flash, a radio signal, a particle, a message, a final observation, once it belongs to the region inside the horizon, it cannot reach the distant universe. Nothing material has to block it. The geometry itself decides. This is why the horizon can be difficult to respect in language. We want it to be a thing. We want to imagine a surface because surfaces are familiar. A surface can be touched. A surface can be crossed. A surface can be photographed from outside. It gives the mind something solid. But the event horizon is more like a decision made by space-time. Outside it, some future paths still lead outward. Inside it, none do. Nothing at the boundary has to push burn or break the traveler. The change is written in the set of possible futures. It is less like hitting a wall and more like passing a point in a river, where every current, no matter how you turn, leads toward a waterfall hidden downstream. Even that image is imperfect because a river flows through space, while a black hole reshapes space-time itself. But it helps soften the first misunderstanding. The danger is not simply that the current is strong. The danger is that every route that remains belongs to the current. In ordinary life, we often confuse invisibility with weakness. If something cannot be touched, perhaps it is not real. If something has no material texture, perhaps it is only a mathematical convenience. Black holes correct that intuition. The horizon may have no substance, yet it has consequences more absolute than almost any material surface in nature. A wall can be broken, a metal door can be melted, a mountain can be climbed or drilled through. A horizon is not defeated that way because it is not made of matter. It is made of the structure of cause and effect. That is why the phrase, "no hand can touch," is not only lyrical. A hand can pass the horizon if the body carrying it falls inward. But it cannot touch the horizon as an object cannot feel its surface, cannot test its texture. The crossing is real, yet the boundary is not a thing in the traveler's palm. From the outside, this becomes even stranger. A distant observer sees the falling object grow dimmer and redder. The signal fades. The final moments stretch beyond practical observation. The horizon is approached through light that loses its energy and becomes harder to receive. The crossing in the outside record is never delivered as a simple final scene. The horizon keeps its own timing. To the traveler, the crossing has already happened. To the outside, the message never arrives in that clean form. The event horizon is therefore not only a boundary in space, it is a disagreement between stories, a place where the universe refuses to give every observer the same narrative in the same way. This prepares the ground for everything that follows, because once observers can disagree so deeply about what is seen, and once information can disappear from the outside account while still falling inward in another frame, the black hole has already begun to pressure the meaning of reality. The information paradox does not begin suddenly with Hawking radiation. Its shadow is present earlier in the way the horizon separates what happens from what can be reported. The horizon is quiet, but it is not simple. This is the hardest part to feel. The horizon is not a wall. It is not a shell of fire. It is not a membrane of matter floating around the black hole. A traveler falling toward a very large black hole might cross it without any local alarm, without a physical impact, without seeing a line painted across space. And yet after the crossing, every future path leads inward. To begin gently, we can think about escape velocity. On Earth, a rocket must reach enough speed to escape our planet's gravity. If it is too slow, it falls back. Around a sufficiently compact mass, the escape speed can exceed the speed of light. Since light is the fastest signal nature allows, escape becomes impossible. That picture is useful, but it is only a first step. General relativity gives a deeper view. Gravity is not merely a pull through space. It is the curvature of space-time. Near a black hole, space-time is arranged so severely that all future-directed paths inside the horizon point toward the deeper interior. The issue is not that light is too weak to climb out. The issue is that out no longer belongs to the future in the way it did before. A flashlight inside the horizon does not fail because its beam lacks effort. It fails because every path open to light remains inside. This is where black holes move beyond ordinary intuition. We are used to thinking of space as flexible and time as unavoidable. We can walk north-south, left-right, forward, or back, while time carries us one way. Inside a black hole, the inward direction becomes strangely tied to the future. The center is not merely a place one might choose to avoid. In the classical picture, it lies ahead in every possible future path. No engine can choose a different tomorrow. This does not mean we should picture the horizon as a dramatic gate. The horizon may be locally quiet, especially for a supermassive black hole. The curvature at the horizon can be mild enough that a falling observer feels no immediate catastrophe. The finality is not local violence. It is global consequence. That makes the horizon one of the most subtle boundaries in science. It may not announce itself to the traveler, but it divides the universe into regions that can still communicate and regions that cannot. Outside events can become part of the shared cosmic story. Inside events continue, but their story cannot be sent back. This is why the phrase event horizon is so precise. An event is something that happens somewhere and somewhen. A horizon is a limit to what can be known or reached. Together, the phrase names the limit beyond which events cannot be observed by the outside world. They may occur. They may have order. They may be meaningful to whatever falls in. But they do not become news for the rest of the universe. From outside the horizon is the last boundary of possible testimony. From inside, it is already behind you. This double perspective creates one of the classic strange features of black holes. To a distant observer, an object falling toward the horizon appears to slow down. Its light becomes redder and dimmer. Signals arrive more delayed, more stretched, more faint. The object seems to fade near the edge, but for the falling object, time continues normally along its own path. It crosses the horizon in a finite amount of its own proper time. It does not experience itself frozen at the edge. Its clock ticks. Its instruments continue. Its fall proceeds. Both descriptions belong to relativity. They are different ways of slicing the same space-time story. There is no single universal clock that all observers must share. Near a black hole, the relationship between time-light and observation becomes part of the mystery. A black hole separates perspectives before it destroys matter. This will matter later when we ask what happens to information. If an outside observer never receives the full final message, while the falling object continues inward, how should the story be counted? What does the outside universe retain? What does the horizon hide, or perhaps encode? For now, the classical answer is simple enough to be haunting. The horizon hides the interior. General relativity can describe the exterior, and in idealized cases, the interior path. But the outside observer cannot receive a signal from beyond the horizon. The black hole's inner region becomes inaccessible to direct astronomical observation. We can reason about it, calculate, model, and test the exterior geometry, but the inside is sealed by causality. This is why the Event Horizon Telescope image is both powerful and incomplete. It shows how light behaves near the boundary. It confirms the shadow predicted by strong gravity. It helps test whether the exterior matches general relativity. But it cannot show what happens after crossing. No telescope can gather light from a region from which light cannot escape. A better telescope can sharpen the shadow. It cannot turn the horizon into a window. That lesson is humbling. Science often advances by seeing farther, larger mirrors, wider baselines, deeper surveys, more sensitive detectors. Black holes remind us that some limits are not merely technological. Some limits are built into the causal structure of the universe. The event horizon is not just a challenge to our instruments. It is a statement about what can reach us. Still, this does not make science helpless. It makes science more creative. If we cannot see inside, we study the boundary. If we cannot receive a signal from beyond it, we observe the last light before the crossing. We map the motion of stars outside. We model gas near the edge. We detect the gravitational waves produced when black holes merge. We ask what laws must hold if the horizon exists. The boundary changes the method of inquiry. It forces language to become precise. We must distinguish the shadow from the horizon from the singularity, the outside from the inside, the traveler's time from the distant observer's time. A careless image can make a black hole seem simpler than it is. The horizon teaches restraint. It asks us not to imagine a physical wall where the theory gives a causal boundary. It asks us not to confuse the glowing ring with the dark interior. It asks us not to think mystery has ended just because a silhouette has appeared. A horizon no hand can touch. The phrase is poetic, but it is also physically honest. There is no material layer to grasp, yet the boundary changes every possible future for whatever crosses it. It does not resist the hand. It removes the hand from the outside universe's future story. A traveler could pass it before understanding what had been lost. Behind them, the route back to the stars would be closed. Ahead, the black hole's interior would no longer be a distant abstraction. It would be the only future direction available in the classical geometry. This is where the journey must move next. We have watched stars reveal an invisible weight. We have seen the shadow of that weight against light. We have approached the horizon and found not a wall, but a boundary in causality itself. The next question is more intimate. What would it mean to cross not through a telescope, not through the image of a ring, but as a thought experiment guided by physics and limited by the mysteries that still remain? What would a falling observer see? What would the outside universe see? How would time behave near the point of no return? And when the horizon is finally behind you, what remains ahead? To imagine falling into a black hole, we have to be careful with imagination. The subject invites exaggeration. It is easy to picture a roaring tunnel, a visible gate, a flash of light, or a violent wall in space. But the real strangeness is quieter. In the physics, we trust crossing the horizon of a large black hole may not feel like passing through a surface at all. The terror is not always in the crossing. It is in what the crossing means. Imagine a small spacecraft falling toward a supermassive black hole. For the sake of the thought experiment, imagine the surrounding environment is quiet without a deadly accretion disk or intense radiation nearby. We are not designing a real mission. We are isolating the geometry, allowing the black hole's space-time to stand clearly before us. Far away, the stars still shine. The wider universe still spreads in every direction. At first, motion and time may seem familiar enough. Then the sky begins to change. Light from stars behind the black hole bends around the dark region. Familiar constellations would no longer remain in their simple shapes. Some regions of the sky might seem compressed or brightened. Some light might take strange curved paths before reaching the traveler. The black hole is not merely an object in the view. It is a lens through which the whole universe is being rearranged. As the spacecraft falls closer, space-time becomes part of the scene. The traveler is not moving through a passive stage. The stage itself is curved, and every beam of light follows the paths that curvature permits. Near the horizon, the outside universe may appear distorted, gathered, shifted, and bent into forms no ordinary journey could produce. Yet if the black hole is large enough, the traveler may feel nothing special at the exact crossing. This is one of the most surprising facts. For a small black hole, tidal, forces near the horizon could be enormous. Gravity would pull much more strongly on the side of the body closer to the black hole than on the side farther away. But for a supermassive black hole, the horizon can be so large that the difference in gravity across the traveler's body at the crossing is much smaller. No alarm has to sound, no line has to glow, no physical shell has to strike the hull. The horizon is crossed because the shape of the future has changed. Behind the spacecraft, the path back to the outside universe is no longer available. Ahead, all future-directed paths lead deeper inward. The traveler can still think, measure, breathe, if life support allows, and watch clocks tick normally in their own frame. But escape has lost its meaning. From the traveler's perspective, the crossing happens in a finite time. Their onboard clock continues. They do not experience themselves frozen on the horizon. They go through. For a distant observer, the same event looks different. Signals from the falling spacecraft take longer and longer to arrive. The light becomes stretched toward redder wavelengths. The images grow dimmer. Each message appears more delayed than the last. To the observer far away, the spacecraft seems to slow near the horizon and fade into darkness. The outside observer never receives a clean final signal that says I have crossed. This is not a simple optical illusion. It comes from relativity. Time does not flow as one universal river measured identically by all observers. Near a black hole, the paths of light and the rate at which signals arrive become deeply distorted. The falling observer and the distant observer both tell valid stories, but their stories do not fit into everyday intuition. A black hole does not only divide space, it divides descriptions. This separation is central to the mystery. The traveler crosses the horizon. The outside observer sees the traveler fade. One account continues inward, the other loses the signal. The same physical situation has two perspectives, and later, when quantum theory enters, that split becomes even more troubling. For now we stay with the fall. The phrase point of no return is more precise than it first sounds. Outside the horizon, return may be difficult, but possible in principle. A powerful enough rocket used before crossing and under the right conditions could still escape. Inside, no engine can restore that option. The problem is not fuel. It is not determination. It is the structure of space-time. Every future path remains inside. In ordinary life, a point of no return is practical. A plane has flown too far. A ship has entered dangerous weather. A climber has gone beyond easy retreat. But in those cases, returning remains physically conceivable. The limits are human mechanical or environmental. Inside a black hole, the limit is causal. Causality means what can influence what. Outside the horizon, an event can still affect distant regions by sending light or some other signal. Inside it cannot influence the outside universe in that direct way. The traveler may still have experiences, but those experiences cannot become part of the external record. This is one of the loneliest ideas in physics. Not loneliness as emotion, but loneliness as geometry. Events may happen behind the horizon. Clocks may tick. Matter may move. The traveler may see, think, and measure for a time. But no report from that region can reach the galaxy again. The outside universe is no longer an audience. Deeper inside, the fall becomes more physically severe. Tidal forces grow. The side of an object closer to the black hole is pulled more strongly than the side farther away. The object stretches along the direction of fall and compresses sideways. This effect is often called spaghettification. The word sounds almost playful, but the physics is not. It is tidal stretching caused by a steep gravitational gradient. Around a stellar mass black hole, it can become fatal before or near the horizon. Around a supermassive black hole, it may become severe only well after the crossing. The timing depends on mass spin trajectory and environment. The important distinction is this: the horizon and the destruction are not the same thing. The horizon is the causal boundary. Tidal destruction is a physical effect of gravity's change across distance. Popular images often merge them into one dramatic moment, but the real physics is subtler. The most important boundary may be crossed quietly, while the most violent consequences come later. If the black hole rotates, as real astrophysical black holes almost certainly do, the picture becomes richer. A rotating black hole drags space-time around with it, an effect called frame dragging. Outside the horizon lies a region known as the ergosphere, where space-time is pulled so strongly in the direction of rotation that nothing can remain perfectly still relative to distant stars. The black hole becomes a rotating geometry. This does not make it a simple whirlpool, though the analogy can help at first. Space-time is not a fluid but near a spinning black hole. The available paths for matter and light are twisted by rotation. The black hole is not merely a dark center. It is a moving shape in the structure of space-time. That rotation matters outside the horizon as well. Magnetic fields, accretion disks, and spinning space-time can help drive powerful jets from the regions around some black holes. These jets do not come from inside the horizon. They arise from the environment, just outside where plasma magnetism and gravity interact with extraordinary energy. The same pattern returns. The interior stays silent. The surroundings speak. As the imagined traveler falls, the details depend on the particular black hole. A quiet, isolated black hole is different from an active galactic nucleus. A stellar mass black hole is different from a supermassive one. A non-rotating ideal case is different from a spinning black hole with an accretion disk. No single fall represents all possible falls. But the core lesson remains. Crossing the horizon does not have to look like the dramatic moment our minds expect. It may be the quiet loss of all possible return. A boundary that cannot be locally felt can still be absolute in its consequence. The universe does not label its deepest thresholds. It gives consequences. For the distant observer, the falling object fades. Its light reddens. Its signals become delayed and weak. In practice, it disappears from view. The outside universe never watches the traveler continue to the center. The horizon becomes the last readable page. For the traveler, the book continues. This split prepares the ground for later mysteries. If the outside observer never receives the full account, where is the information? If the falling object crosses and continues inward, what happens to the details that made it unique? If the black hole later radiates, can any trace of those details return? Those questions wait ahead. For now, the classical path moves inward. The horizon is behind. Tidal forces increase. The sky distorts. The future narrows. The center is no longer simply a place in space. In the simplest classical picture, it becomes something like an unavoidable future boundary. No turn avoids it. No signal returns. This is where our thought experiment reaches its limit. We can describe the horizon. We can compare observers. We can explain redshift tidal stretching and the quiet finality of causal separation. General relativity can guide us inward for a time. But deeper inside, the theory points toward a region where curvature grows without bound. The question changes again. What happens when the equations that led us so far begin to lose their voice? Is there truly a singularity, or does that word mark the place where our present theory breaks down? Does the black hole end in a physical point or in a missing theory? The traveler cannot return. The equations are all we have, and even they begin to tremble. After the horizon, the story becomes harder to tell. Not because nothing happens, but because whatever happens no longer sends a report back to the outside universe. A traveler who crosses the point of no return continues inward in their own time. The distant observer receives only fading signals. The black hole becomes from outside a region of disciplined silence. Inside that silence, classical general relativity points toward a warning. The warning is called a singularity. The word can sound like a place, as if a tiny point waits at the center, packed with all the matter that ever formed or entered the black hole. Popular descriptions often speak of infinite density at zero volume. That image captures something about the extremity of the prediction, but it can also make the singularity sound too much like an ordinary object. In serious physics, a singularity is better understood as a sign that the description has reached its limit. Space-time itself becomes incomplete. Paths that falling matter could follow cannot be extended indefinitely. Curvature may grow without bound. Quantities used by the theory cease to behave in a physically meaningful way. The problem is not merely that matter becomes dense. The problem is that the stage on which matter moves seems to break down. This is why the singularity is so haunting. It is not only a mystery inside a black hole. It is a message from one of our greatest theories, saying I cannot continue in the same language. For much of the journey so far, general relativity has been our guide. It explained how gravity bends light. It gave black holes their geometric meaning. It described horizons as causal boundaries. It helped us understand why a falling observer and a distant observer tell different stories near the point of no return. Then the same theory carries us inward and points toward a place it cannot fully describe. That does not make general relativity weak. It makes the warning more serious. A fragile theory can fail in ordinary situations. General relativity has survived extraordinary tests. It has explained the orbit of Mercury, the bending of starlight, gravitational time dilation, gravitational lensing, black hole shadows, and the ripples in space-time we call gravitational waves. When such a theory reaches a limit, the limit matters. Early black hole solutions were often highly idealized. Perfect spherical symmetry, no rotation, clean mathematics. One could reasonably wonder whether the singularity appeared because the model was too neat. Real stars rotate, churn collapse, unevenly carry magnetic fields, and interact with their surroundings. Perhaps nature would avoid the mathematical catastrophe. That hope did not disappear immediately. Science had reason to be cautious. A strange feature of an equation does not automatically become a physical object. Exact solutions can teach us, but they can also depend on special assumptions. The question was whether singularities were artifacts of simplified models or serious predictions of gravitational collapse. Roger Penrose changed that question. Penrose showed that under broad conditions, once a trapped surface forms general relativity, leads toward geodesic incompleteness. The phrase is technical, but the meaning is profound. It suggests that the breakdown is not only a quirk of perfect symmetry. If enough mass collapses in the right way, the theory itself points toward an end to ordinary space-time paths. The singularity became harder to dismiss. Penrose's work matters not only because it strengthened the case for black holes, but because it changed the emotional status of the singularity. It was no longer easy to comfort oneself by saying that only an unrealistic, perfectly spherical star would lead to such a strange end. The mathematics suggested something deeper: collapse itself under broad conditions, could create regions from which the future could not be extended in the familiar way. This did not make the singularity visible. It made the problem unavoidable. A useful way to feel this is to imagine a map that works beautifully across an entire continent. It marks rivers, mountains, roads, cities, coastlines, and valleys with astonishing precision. Travelers trust it because it has guided them again and again. Then at the edge of one region, the map does not merely become vague. The lines converge into a place where the idea of a road no longer makes sense. You would not say the map was worthless. You would say it had brought you to the edge of what it could describe. General relativity is something like that near a singularity. It is not wrong in the ordinary sense. It has guided physics through immense distances and subtle tests. It has allowed us to predict how clocks run in gravitational fields, how light bends, how orbits shift, how waves ripple through space-time. But when followed into the deepest interior of a black hole, it leads to a boundary where the smooth space-time it assumes appears to fail. This makes the singularity different from ordinary ignorance. Ordinary ignorance is a blank space we have not yet explored. The singularity is a blank space created by a theory that has been too successful to ignore. It is as if the theory itself walks us to the edge points into the dark and says that the next step requires another language. That is why physicists do not treat singularities casually. They are warning signs. They indicate that some essential ingredient may be missing. Perhaps quantum effects cannot be ignored. Perhaps space-time is not infinitely divisible. Perhaps the smooth geometry of relativity is an approximation that breaks down at extreme curvature. Perhaps the interior is replaced by something no classical diagram can honestly show. The difficulty is that all of these possibilities remain hidden behind the horizon. In many areas of science, when a theory fails, experiments can push directly on the failure. A particle accelerator can explore higher energies. A telescope can look deeper. A detector can become more sensitive. But the singularity inside an astrophysical black hole is not a laboratory we can access. No probe can return. No light can climb out with a report. No photograph can show the center. The black hole gives us the problem, then hides the experiment. This is part of the reason black holes feel so philosophically powerful. They do not merely test what we know, they test how we know. They ask what kind of science can be done when direct observation is blocked by the structure of the universe itself. They ask how far inference can go, how much mathematics can be trusted, and where a successful theory must be held with both confidence and caution. A singularity, then, is not just an endpoint in a diagram. It is the place where certainty changes texture. Later, Stephen Hawking extended related ideas into cosmology, connecting singularity theorems with questions about the beginning of the universe. Black holes and the Big Bang are not the same, but both press general relativity into extreme regimes. One looks inward toward collapse. The other looks backward toward an early state of immense density and curvature. In both directions, the theory reveals more than it can finish. This is the strange power of the singularity. It is hidden from view, yet it exposes something about the boundary of knowledge. It cannot send light outward, but it sends a problem outward through mathematics. It sits behind the horizon, but it shapes the entire meaning of the black hole. The center is hidden. The question is not. This is where the idea of cosmic censorship enters the story. The phrase sounds almost mythic, as if the universe were deciding what may be seen. In broad terms, the cosmic censorship conjecture suggests that singularities formed by realistic gravitational collapse are hidden behind event horizons, rather than exposed to the outside universe. If that is true, nature may protect distant observers from seeing the breakdown directly. The region where classical predictability fails would be wrapped inside a horizon. The outside universe would still be governed by equations that behave well. Stars could orbit, gas could glow, black holes could merge, shadows could be imaged. The most dangerous part of the geometry would remain concealed. But cosmic censorship is not a fully settled law. It is a conjecture, a deep and difficult question in mathematical relativity. Physicists have studied whether naked singularities not hidden behind horizons, could arise under certain conditions. The details are technical and subtle. For our journey, the essential idea is enough. Perhaps nature usually hides the places where the classical theory breaks, but we do not know that this must happen in every possible case. The black hole becomes a curtain. On one side, the outside universe can be studied with extraordinary precision. On the other side, the equations point towards something that cannot be treated as an ordinary place. The curtain is real, and what it conceals remains unfinished in physics. This is why we should speak carefully about inside a black hole. The phrase can make the interior sound like the inside of a cave, a room, or a planet. If only we had the right instrument, we imagine we could map it. But in the classical picture, the interior of a black hole is not simply a hidden chamber. It is a region where the usual roles of space and time become deeply unfamiliar. Inside a simple non-rotating black hole, the singularity lies in the future of every falling path. That sentence deserves to be heard slowly. The singularity is not just a dot one can steer around. Once inside the horizon in the classical geometry, the central end is unavoidable in the way the future is unavoidable. The analogy is imperfect, but it gives the mind a way to feel the strangeness. The singularity is less like an object waiting at a location and more like a boundary toward which all future-directed motion leads. In ordinary life, danger can be avoided by choosing a different path. A ship can steer around rocks. A climber can avoid a cliff. A spacecraft can adjust course. Inside the horizon, that ordinary freedom is gone. The problem is not bad navigation. It is the structure of space-time. And then, according to the classical theory, the path ends. We should not pretend this is the final physical truth. Quantum gravity may change the story. The singularity may be resolved, replaced, softened, or transformed by a deeper theory. Space-time itself may not continue to be smooth at such scales. The idea of a central point may belong more to the limit of our equations than to nature's final answer. The honest position is quieter than the popular image. Classical general relativity predicts a breakdown. The full physical meaning of that breakdown remains unknown. That unknown is not vague. It is structured by everything we do know. We know why collapse leads to trapped regions. We know why horizons seal the interior from outside signals. We know why curvature becomes extreme. We know why quantum effects should matter when gravity is intense and scales become small. We know why our current theories are not yet unified. The mystery has a shape. It is not empty darkness. It is a boundary drawn by successful theories that no longer fit together smoothly. General relativity describes gravity as geometry. Quantum mechanics describes matter radiation and fields through probabilities and quantum states. Both are extraordinarily successful in their domains. But the singularity seems to demand both at once. It is a region of extreme gravity, extreme density, and extremely small scales, precisely where neither theory alone should be trusted as the complete account. This is why black holes matter beyond astronomy. They are not only objects in the sky. They are laboratories of principle. They force our best theories into a room together and ask them to describe the same event. General relativity speaks in geometry. Quantum theory speaks in states fields and uncertainty. The singularity asks for a language that has not yet been fully found. Many possible ideas have been explored. Perhaps quantum gravity removes the singularity. Perhaps space-time becomes discrete or emergent. Perhaps the interior bounces transitions or is replaced by a structure no classical diagram can capture. Perhaps the question itself changes when gravity is quantized. These ideas are alive in research, but not settled by observation. No signal has returned from the interior to choose among them. That is part of the discipline of this subject. A louder story would turn the singularity into a portal, a cosmic tunnel, or a definite point of infinite density. A more careful story leaves space for uncertainty. The classical equations lead us toward breakdown. The replacement is not yet known. There is humility in that. Science is often praised for its answers, but some of its deepest strength appears when it can identify the boundary of an answer. It can say, this theory has carried us here. Here is where it stops being enough. The singularity is one of those moments. The silence of the equations is not a failure to think. It is an invitation to think more deeply. This is why the singularity cannot be the end of our journey. It shows that classical gravity is incomplete, but it does not tell us how to complete it. To go further, physics has to bring in heat entropy and quantum theory. And when those ideas approach the horizon, black holes become stranger still. For a long time, a black hole seemed like the coldest possible object, a perfect absorber, the final silence of matter and light. Then Stephen Hawking and Jacob Bekenstein changed the story. The dark object acquired entropy. It acquired temperature. It could, in principle, radiate. The black hole was no longer only a place where equations went silent at the center. Its horizon became part of thermodynamics. And the next question became even deeper. If a black hole can slowly radiate away energy, if it can shrink, if it can one day disappear, then what happens to everything it swallowed? The singularity asks where our equations fail. The next mystery asks whether the universe can forget. A black hole seems at first like the coldest object nature could make. Light crosses the horizon and cannot return. Matter falls inward and disappears from the outside story. A signal sent too late never reaches the rest of the universe. If heat is associated with radiation, and if a black hole allows nothing to escape from within, then it should appear perfectly dark, perfectly cold, and perfectly final. But black holes often break the first picture we make of them. The event horizon changed the meaning of escape. The singularity changed the confidence of classical equations. Then physicists began to ask what happens not only to matter, but to entropy. Entropy can be thought of loosely as a measure of hidden, microscopic possibilities. A cup of hot tea has many ways its molecules can move while still looking like tea. A cloud of smoke carries countless microscopic details. A burned page may no longer be readable, but its atoms, heat, ash, and radiation still belong to the physical universe. The information has been scrambled. It has not simply left reality. Now imagine a book falling into a black hole. From outside, the pages disappear. The letters, ink, paper, fibers, arrangement of atoms, and exact physical state cross the horizon. The black hole's mass changes slightly. Its outside description changes only in a few broad ways. The detailed pattern of the book can no longer send a signal out. Jacob Bekenstein saw a problem here. If the book carried entropy, and if that entropy vanished from the outside universe when the book crossed the horizon, then the second law of thermodynamics seemed threatened. Entropy outside would decrease. A black hole could swallow disorder, and make it inaccessible, as if nature had found a way to hide entropy from the accounting of the universe. That felt physically suspicious. Wittgenstein proposed that the black hole itself must have entropy. When matter falls in, the entropy outside is not simply lost. The black hole's entropy increases. More strangely, that entropy appeared to be proportional not to the volume inside the black hole, but to the area of the event horizon. The boundary became a ledger. This idea also changed the emotional meaning of the horizon. Earlier, the horizon was the place where the outside universe stopped receiving messages. Now it became something stranger, a boundary whose size seemed to keep track of what had happened. Matter crossed inward, and the horizon area increased. Entropy disappeared from outside view, and the black hole's entropy rose. The horizon did not speak, but it responded. That response is one reason black holes began to look less like cosmic graves and more like physical systems with hidden inner accounting. A grave is a place where a story ends. A black hole, in thermodynamic thinking, is a place where the story is transformed into a form we do not yet fully understand. Imagine dropping different things into a black hole, a cloud of hydrogen, a broken satellite, a book, a star, a stream of radiation. To the outside, after the horizon settles, the detailed differences seem largely erased from the classical description. The black hole becomes a little more massive. Its spin may change. Its horizon area changes. But the rich details of the object's previous form are no longer available. The horizon area becomes the only visible hint that something has been added to the hidden account. This is unsettling because it reduces enormous complexity to a simple change in geometry. A library and a cloud of gas may be radically different before crossing the horizon, but if they carry the same mass energy, angular momentum, and charge, the final black hole may look the same from far away. The outside universe loses the details. Yet thermodynamics insists that details cannot be ignored so easily. Entropy is the language of hidden detail. It allows physics to speak about what is not individually tracked. When Wittgenstein connected entropy to horizon area, he gave the black hole a hidden depth. The smooth, featureless boundary was no longer empty in meaning. It became a measure of possible microscopic states, even if no one yet knew exactly what those states were. This was a strange kind of progress. Instead of showing us what the black hole contains, it told us that there must be something to count. The area law also created a quiet revolution in how physicists think about space. In ordinary intuition, a bigger volume can hold more information because it contains more places for things to be. But black holes suggested a different limit. The maximum entropy of a region seemed tied to boundary area. The edge mattered more deeply than anyone had expected. This is the seed from which later holographic thinking would grow. But before that seed became a larger framework, Hawking's calculation gave the story a new turn. If the black hole has entropy and temperature, then it radiates. If it radiates, it loses energy. If it loses energy, it may eventually shrink away. The ledger is not fixed forever. The account may close, and that is where the information paradox becomes unavoidable. This was a startling idea. Most objects seem to store entropy in their volume. A gas fills a box. A star contains layers of plasma radiation pressure and motion. But the entropy of a black hole appeared to scale with area, with the size of the horizon. The region that hides everything also seemed to count something. At first, this idea created another puzzle. If a black hole has entropy, thermodynamics suggests it should have temperature. If it has temperature, it should radiate. But a black hole was supposed to be black. Nothing from inside the horizon could return. Then Hawking performed the calculation that changed the field. When quantum field theory is considered in the curved space-time around a black hole, the result is remarkable. An observer far away should see a faint thermal radiation associated with the black hole. This radiation does not come from matter escaping after crossing the horizon. It arises from the quantum behavior of fields in the black hole's space-time. The black hole is not completely black. It has a temperature. This radiation, now called Hawking radiation, turned black holes into thermodynamic objects. They were no longer only geometric structures in general relativity. They had entropy, temperature, and a way to lose energy. In principle, a black hole could shrink over time. For astrophysical black holes, the effect is incredibly faint. A black hole with the mass of a star is colder than the cosmic microwave background today. A supermassive black hole is colder still. Such black holes are not glowing visibly in the sky because of Hawking radiation. In ordinary cosmic environments, they absorb far more energy than they lose. But the idea matters because of what it reveals. A faint theoretical radiation can transform the foundations of physics. If black holes radiate, then over inconceivably long timescales, they may evaporate. The larger the black hole, the colder it is, and the slower it evaporates. Smaller black holes are hotter. If an isolated black hole lost mass through Hawking radiation, its temperature would rise as it shrank, and the process would accelerate near the end. For the black holes we know in the sky, the time scale is far beyond the present age of the universe. Stars will die. Galaxies will fade. The bright era of cosmic history will pass before large black holes evaporate in any meaningful way. Still, the principle changes everything. A black hole is no longer eternal in the simplest picture. It can slowly leak energy. It can participate in a future far beyond stars. It can be part of thermodynamics and quantum theory, not only gravity. Then the old book returns. If a book falls into a black hole, and if the black hole later evaporates through Hawking radiation, what happens to the detailed information in the book? If the radiation is purely thermal and carries no subtle record of what entered, and if the black hole eventually disappears, then the information seems gone. This is the black hole information paradox. It is not really about books. The book is only a way for the mind to hold the problem. The deeper question is whether the universe can erase physical information. In quantum mechanics, the evolution of a closed system is expected to preserve information in a precise sense. Different initial states should not collapse into exactly the same final state, with no way even in principle to distinguish them. A black hole seems to threaten that rule. General relativity says the horizon prevents signals from returning. Hawking's calculation says the black hole radiates thermally. Quantum mechanics says information should be preserved. Thermodynamics says black holes have entropy and temperature. Each idea is powerful. Together they create tension. This is why the paradox has lasted so long. It is not a puzzle born from weak science. It is born from strong theories meeting at their edges. General relativity works extraordinarily well. Quantum mechanics works extraordinarily well. Thermodynamics works extraordinarily well. Black holes bring them into the same room and ask for one story. The first story does not fit. If information is truly destroyed, quantum mechanics must change in a deep way. If information is preserved, then Hawking radiation, the horizon, or the structure of spacetime must be subtler than the simplest picture suggests. Something in the old arrangement has to be revised. Physicists have explored many possibilities. Perhaps information escapes in delicate correlations within the radiation. Perhaps the horizon has microscopic degrees of freedom that encode what falls in. Perhaps spacetime itself emerges from quantum information in ways we do not yet fully understand. Perhaps the classical picture of the black hole interior is only an approximation. The exact answer remains one of the central problems of theoretical physics. The important point for this journey is that the mystery has moved. Earlier, we looked toward the singularity deep inside the black hole as the place where equations went silent. Now the event horizon itself has become mysterious. It is not only a boundary of no return, it is connected to entropy, temperature, and information. The edge has become active. Bekenstein's area law is one reason. A black hole's entropy scales with the area of the horizon. This suggests that the boundary somehow counts hidden states. It hints that the information associated with a region may not be stored in the way ordinary volume-based intuition expects. Here begins the path toward holographic thinking. The word holographic can be dangerous if used carelessly. It does not mean that the universe is fake in the ordinary sense, or that a black hole is literally a screen like a cinema wall. The deeper idea is that information in a volume may be describable by degrees of freedom on a boundary. Black holes made this idea hard to ignore because their entropy follows area. The horizon, once understood as the end of messages, begins to look like a surface of accounting. Not a material surface, not an ordinary storage device, but a clue. This is one of the most beautiful reversals in black hole physics. The same boundary that seems to hide the interior may also be connected to the rules that preserve what falls in. The horizon silences ordinary signals, but its area responds. It prevents direct return, but it may participate in a deeper form of memory. A black hole no longer looks like a cosmic drain. A drain merely removes. A black hole turns removal into a question about reality. Somewhere in the dark, between stars, an isolated black hole may appear almost perfectly still. No glowing disk, no jet, no nearby star being torn apart. It may seem to be the purest form of cosmic silence. Yet in theory, it has temperature. It has entropy. It is part of a thermodynamic story stretching across times far beyond the age of galaxies. The quietest object becomes one of the loudest questions. What is heat when the object has no ordinary surface? What is entropy when the interior cannot be observed? What is information when the horizon prevents return? What is time when a black hole can evaporate across ages beyond imagination? These questions gather at the boundary. The event horizon began as a limit to escape. Bekenstein tied it to entropy. Hawking tied it to radiation. The information paradox made it a meeting place for gravity, quantum mechanics, and thermodynamics. The same invisible boundary now carries the weight of several unfinished theories. The next section must stay near that boundary. If information is not destroyed, where is it? If the horizon has entropy, what does it count? If the radiation eventually carries information, how can it do so without breaking the causal silence that made the black hole a black hole? The question is no longer only whether the universe can forget. It is whether the memory of what falls in is somehow written at the edge. If the horizon can carry entropy, then the edge of a black hole is no longer just an edge. It becomes a place of accounting, a boundary that seemed to hide the details of falling matter begins to look in a deeper theory as if it must somehow preserve them. The event horizon remains silent to ordinary signals, but its area changes when something enters. It grows when energy falls in. It responds. The door does not open, but perhaps the boundary remembers. This is the strange shift produced by black hole thermodynamics. At first, the deepest mystery seemed to lie at the singularity where classical equations lose their voice. Then, Hawking radiation and Bekenstein entropy moved part of the mystery outward. The horizon itself, the line no hand can feel, became a place where gravity, heat, and information meet. A black hole now looks simple and impossibly complex at the same time. From far away, a stationary black hole can be described by very little. In the simplest classical picture, it has mass, spin, and electric charge. Real astrophysical black holes are not expected to carry much net charge for long, so, in practice, the main outside properties are mass and spin. This is connected to the phrase, "black holes have no hair." The phrase is playful, but the idea is severe. A star is rich with details, layers, chemistry, turbulence, magnetic fields, age, and history. A planet has mountains, storms, minerals, oceans, scars, and rotation. A book has pages, ink, words, meaning, and an exact arrangement of atoms. If all of these fall into a black hole, the outside description seems to keep only a few broad quantities: mass, spin, perhaps charge. The details appear to vanish from the accessible story. Quantum mechanics resists that disappearance. In ordinary quantum theory, information is expected to be preserved in a precise sense. It can become scrambled beyond practical recovery, as when a burned book becomes smoke, heat, ash, and radiation. But scrambling is different from destruction. The information is hidden in correlations not erased from reality. A black hole seems to ask for more than scrambling. It asks what happens when the correlations pass behind a horizon and the black hole later evaporates into radiation that in the simplest view looks thermal. If many different pasts produce exactly the same final radiation, then the universe has lost distinctions it should have kept. For quantum mechanics, this is not a minor inconvenience. It is a threat to the structure of the theory. Every possible escape seems to disturb something important. If information is destroyed, quantum mechanics must be changed. If information escapes the horizon, must allow the outside to recover details that seemed trapped. If the horizon remains perfectly smooth for the falling observer, then the mechanism of recovery becomes hard to understand. If the horizon becomes violent, the classical picture of falling through it is damaged. Black holes force physics to choose carefully. One of the most influential clues remains the area of the horizon. Black hole entropy depends on area, not volume. This single fact suggests that the boundary is tied to the number of possible hidden states. The interior may be strange and inaccessible, but the counting of possibilities seems connected to the surface. This is where the holographic idea begins to glow. A hologram in ordinary experience is a surface that can encode the appearance of a three-dimensional image. The physics inspired by black holes is much deeper, but the broad intuition is this: perhaps the information in a region of space can be described by degrees of freedom on its boundary. Perhaps volume is not the deepest way nature stores or counts reality. For black holes, this is not a decorative metaphor. It grows from the horizon area itself. The holographic principle has been made precise in certain theoretical settings, especially where gravitational theories in one kind of space-time are related to quantum theories on a boundary. But our universe is not simply identical to every idealized model where the mathematics is clearest. The idea is powerful and suggestive, but it should not be treated as a finished explanation of every real black hole in the sky. Still, it changed the direction of thought. Instead of asking only what is inside the black hole, physicists began asking whether the inside might be encoded differently from what common sense expects. Instead of treating the horizon as a passive limit, they began seeing it as a clue. The surface that hides may also preserve. For a listener, it may help to slow the idea down with a gentler image. Imagine a sealed room that no sound can escape from. People outside cannot hear what happens inside. They cannot see inside. They cannot receive a message from anyone who enters. But every time something enters the room, the size of the door changes by a precise amount. The room remains sealed, yet the door somehow records that the room's hidden possibilities have changed. A black hole horizon is not literally such a door, but the analogy shows the tension. The boundary blocks ordinary communication, yet its area behaves as if it is tied to the hidden accounting. That is why the horizon becomes so important. It is the last place available to the outside world, and also the place where thermodynamics leaves its mark. This makes the information paradox feel less like a remote puzzle and more like a question about memory. What does it mean for the universe to remember something? In daily life, memory requires a visible trace, words on paper, marks on stone, patterns in a brain, bits on a drive. In physics, memory is more general. It means that the present state of the world still contains, at least in principle, enough structure to distinguish one possible past from another. A black hole threatens this distinction. If a star falls in and a cloud of gas falls in and the final black hole looks identical except for the same broad quantities, then the outside description has lost the difference. If the black hole later evaporates into featureless radiation, the difference seems gone not only in practice, but in principle. That is the dangerous part. Physics can tolerate secrets. It has trouble tolerating true erasure. This is why the black hole information paradox has become more than a technical dispute. It asks whether the universe is fundamentally reversible at the quantum level, or whether gravity can introduce a deeper kind of forgetting. It asks whether space-time geometry is enough to define reality, or whether information must be placed closer to the foundation. The surface of the black hole becomes the meeting place for these questions, because it is where all the contradictions gather. The interior cannot report. The exterior must still obey quantum rules. The horizon has area and entropy. Hawking radiation carries energy away. The black hole may eventually vanish. If it vanishes, the account must be settled somehow. The paradox is not a single locked box. It is a set of doors that all seem to close at once. This is why different proposals can sound so strange. Firewalls, fuzzballs, holography islands, complementarity, page curves. Each tries in its own way to prevent one part of physics from breaking while respecting the power of the others. The names can be distracting, but beneath them lies a shared pressure. Black holes demand that gravity and quantum information be reconciled. The exact solution remains unfinished, but the direction of the lesson is already profound. The horizon may be less like an empty line in space and more like a place where the deep rules of reality become visible in coded form. To understand it fully may require understanding why space-time heat and information are linked at all. The surface hides the room, but it may also carry the only clue to the room's contents. But a beautiful idea is not enough. It has to fit with everything else. It must respect the success of general relativity outside the horizon. It must preserve quantum information. It must reproduce black hole thermodynamics. It must explain why, for a large black hole in the classical picture, a falling observer might cross the horizon without local catastrophe. That last point creates another tension. General relativity suggests a smooth horizon for a large black hole. A freely falling observer should not encounter a physical wall exactly at the crossing. This is part of the calmness of Section 4. The horizon is final in consequence, but not necessarily violent in local experience. Yet some attempts to preserve information have led to a more disturbing proposal. Perhaps the horizon is not smooth after all. Perhaps an infalling observer would meet a high-energy barrier, a so-called firewall. The firewall idea arose from efforts to hold together quantum information, Hawking radiation, and the structure of entanglement. It is not an observed feature of real black holes. It is a sign of how difficult the paradox has become. The smooth horizon may not be easy to protect. The firewall proposal remains controversial, and for this journey, it should be understood as a warning, not as a settled answer. It shows that the information paradox is severe enough to make physicists question even the peaceful crossing predicted by classical relativity. Other ideas change the interior more radically. In some string theory-inspired approaches, including fuzzball proposals, what looks like a black hole from far away may correspond to many horizon-scale quantum states. The classical empty interior and singularity might be replaced by detailed microstructure. The name can sound informal, but the motivation is serious: preserve information and remove the singularity by changing what the black hole really is at microscopic scales. Again, caution matters. These are not confirmed descriptions of Sagittarius, a star, or M87 star. They are theoretical attempts to understand what a quantum black hole could be. Their value here is that they reveal the range of possibilities forced open by the paradox. If the old interior creates a contradiction, perhaps the old interior is not the final picture. The black hole becomes less like a hole and more like a compressed library whose pages cannot yet be read. Another major development comes from the Page curve. Don Page asked what should happen to the entropy of Hawking radiation if information is preserved during evaporation. At first, the radiation should become more entangled with the remaining black hole, and its entropy should rise. But after a certain point, if the process is unitary, the radiation must begin to reveal correlations, and the entropy should fall. This gives physicists a target. If information survives, the radiation should not remain featureless forever. It should contain subtle structure. In recent theoretical work, especially in simplified gravitational models, using ideas called islands, calculations have reproduced a page-like curve. These results suggest that information loss may not be inevitable when gravity is treated more carefully. But they are mathematical progress, not a telescope image of an evaporating black hole. They do not mean we have watched a real astrophysical black hole release its stored history. They show that in certain controlled settings, the union of quantum theory and gravity may preserve information after all. They point towards something deep in the relation between space-time entanglement and the boundary between inside and outside. The technical details can become dense, but the emotional shape is clear. For decades, black holes seemed to divide the universe into two stories. Outside, the story could be measured. Inside, the story could not return. Quantum information says those stories cannot be completely independent if the full process obeys quantum rules. Somehow the outside must account for the inside. That sentence is not a solution. It is the tension. How does the outside account for the inside? Through correlations in Hawking radiation, through horizon degrees of freedom, through holographic encoding, through quantum structure, replacing the classical interior, through a theory not yet complete. The answer remains open, but black holes have made one thing impossible to ignore. Geometry and information are not separate subjects at the horizon. The horizon is where light fails, but physics continues to ask what reality is made of. This is also why the no-hair idea is so haunting. From far away, the black hole looks almost featureless, yet its entropy is enormous. It is as if the object wears a plain mask while hiding a vast number of possible microscopic histories. The exterior says the black hole is simple. The entropy says it is not. A blank face, an unreadable archive. If information survives evaporation, then the archive may eventually be scattered into radiation, not as readable pages, not as a message floating outward, not as an easy reconstruction. The information may be scrambled so thoroughly that no realistic observer could ever recover it. But practical impossibility is not the same as fundamental destruction. A burned book cannot realistically be reconstructed from smoke. A black hole may be far worse. But if quantum theory is right, difficulty is not erasure. The universe may preserve distinctions in ways that are nearly impossible to decode. The black hole may not be a place where memory ends. It may be a place where memory becomes hidden in the deepest correlations nature allows. This gives the paradox a strange calmness. The black hole does not shout an answer. It forces patience. It tells us that the deepest layer of reality may not be matter moving through a ready-made space, but information entanglement, geometry, and thermodynamics woven together. Perhaps space-time itself is not the first ingredient. Perhaps it is something that emerges. That possibility remains far from a final answer. But black holes have made it thinkable. They have turned horizons into clues, entropy into geometry, radiation into a question about memory, and darkness into a laboratory for quantum gravity. The greatest mystery hidden inside a black hole may not be a hidden object. It may be a rule about what the universe is allowed to lose and what it must keep. A rule about whether information is more fundamental than geometry. A rule about whether the interior of a region can be encoded on its boundary. A rule about whether Einstein's smooth space-time is the deepest structure or only the calm surface of something quantum beneath it. This is why black holes remain central even for physicists who never point a telescope. They are not only astronomical objects, they are thought experiments made real by the cosmos. They take equations seriously enough to expose where equations disagree. They force the outside and inside the surface and volume, the classical and quantum, to meet at the same boundary. The paradox is written on the surface because the surface is where these tensions gather. But our journey is not finished at the horizon. We have moved inward for a long time. Stars revealed an unseen mass. Shadows revealed the shape of darkness. Horizons divided cause and effect. Falling observers carried us past the point of no return. Singularities exposed the limits of classical gravity. Hawking radiation made darkness warm. The information paradox turned the horizon into a question about memory. Now the direction changes. Black holes are not only final states, they are also part of cosmic beginnings. Some of the most puzzling black holes in modern astronomy are enormous objects seen when the universe was young, perhaps too young for them to have grown by the simplest routes. If black holes are places where knowledge reaches a boundary, then the first such boundaries may have appeared surprisingly early. The final section looks back toward cosmic dawn, where another mystery waits. How did the darkness grow so large so soon? After the paradox at the horizon, the journey turns outward again. For a long time, we have moved inward from stars around Sagittarius, a star to the black hole, shadow to the horizon, to the fall, to the singularity, to Hawking radiation, and to the question of information. The black hole has become less like a simple object and more like a meeting point for the deepest unfinished ideas in physics. But black holes do not belong only to endings. They also appear in the story of beginnings. Far beyond nearby galaxies, light from the young universe is still traveling toward us. It has crossed billions of years of expansion. It has been stretched into infrared wavelengths. It arrives faint red and ancient, carrying traces from a time when the first galaxies were still forming. For most of human history, that era was unreachable in detail. The universe before the first stars was dark. Then came cosmic dawn. Gas gathered under gravity. The first stars ignited. Young galaxies began to assemble from smaller structures. Matter slowly arranged itself into the long web that would one day hold galaxies' clusters and filaments. Inside that early light, astronomers have found another puzzle. Some black holes seem to have grown very large, very quickly. In the modern universe, supermassive black holes sit at the centers of many galaxies. Sagittarius. A star has about 4 million solar masses. M87 star has billions. Quasars and active galactic nuclei show what happens when gas falls into such giants and releases tremendous energy before crossing the horizon. Nearby, these black holes feel ancient. They seem like products of long histories, accretion mergers, galaxy growth, stellar deaths, and cosmic time. A small black hole forms from a massive star. It feeds. It merges. It grows. Over billions of years, perhaps it becomes enormous. But the early universe offers less time. That is the problem. Astronomers have found quasars, an active galactic nuclei from when the universe was less than 1 billion years old. Observations from the James Webb Space Telescope have sharpened the mystery by revealing distant galaxies and black hole candidates at very early times. Some systems appear to contain black holes that are already surprisingly massive for their young host galaxies. The question is not whether black holes can grow. The question is whether they can grow fast enough. Imagine beginning with the remnant of one of the first massive stars. That black hole might have tens or hundreds of solar masses depending on the star and its depth. To reach millions or billions of solar masses in the first few 100 million years, it would need extreme growth. It would have to feed efficiently, perhaps almost continuously in a young and chaotic universe. But feeding a black hole is not simple. Gas falling inward heats and radiates. That radiation can push back on incoming material. There is a balance often described through the Eddington limit, where the outward pressure of radiation competes with inward gravity. If the black hole feeds too fiercely, the energy released by the feeding can help slow or expel the fuel. A black hole can be hungry. Its meal can fight back. This makes the origin of early supermassive black holes difficult to explain through one simple path. Some models allow rapid accretion under special conditions. Some allow periods of super Eddington growth. Some involve mergers between black holes and galaxies. Some begin with larger initial seeds. Each route carries questions. The young universe becomes a clock, and every massive black hole found too early asks whether our clock is missing a shortcut. One possible shortcut is the heavy seed idea. Instead of starting with a small black hole left behind by a dead star, perhaps some black holes began much larger. Under rare conditions, a massive gas cloud might collapse directly into a black hole or form a supermassive star that quickly collapses. Such a seed could begin with thousands or tens of thousands of solar masses, perhaps more. This changes the story. A black hole would not always be the final remnant of a star. Some early giants may have formed from gas that avoided ordinary fragmentation, gas that did not break apart into many stars, but collapsed toward one central object. In that case, darkness would not arrive only after a star's death. It could be born large, but direct collapse is not easy. Gas normally cools fragments and forms stars. To collapse into one massive central object, it must follow a special path. Radiation from nearby stars, primordial chemistry turbulence, angular momentum, heavy elements, and the structure of early dark matter halos may all matter. The conditions are possible in models, but nature must provide them. Another route keeps smaller seeds but feeds them rapidly. The early universe was rich in gas. Young galaxies were dense and unstable. Streams of matter flowed inward. If a black hole sat in the right environment, surrounded by enough fuel, it could grow fast. Periods of super Eddington accretion might allow a small seed to gain mass at a surprising rate. But gas does not fall neatly just because gravity asks. It carries angular momentum. It forms disks. It heats, shines, and pushes back. Star formation, supernovae galaxy interactions, and black hole feedback all disturb the flow. Feeding a black hole is less like pouring water into a hole and more like guiding a storm toward a point while the storm is blazing. This is why early observations matter. They test origin stories against time. If many massive black holes existed, very early heavy seed models gain strength. If smaller black holes are found growing rapidly in large numbers, light seed plus fast accretion remains attractive. If young galaxies contain black holes that seem unusually massive compared with their stars, then black hole growth and galaxy growth may not have been synchronized in the simple way once imagined. The early universe is not only a window, it is a test. The James Webb Space Telescope is especially important because early light has been stretched by cosmic expansion into infrared wavelengths. Webb can examine faint distant galaxies, measure spectra estimate redshifts, and help distinguish light from young stars, from light produced by material falling into black holes. Even then, interpretation is difficult. Some compact red sources in Webb data have sparked debate. Are they small galaxies packed with stars? Are they active galactic nuclei with growing black holes? Are they dusty, dense, unusual systems that combine both? Their color spectra, emission lines, and sizes offer clues. But the first galaxies do not always fit the neat categories built from the nearby universe. This uncertainty is not a flaw in the story. It is the story. The first black holes are difficult to identify because they are buried in the first cities of stars. A young galaxy may glow from newborn stars, heated gas dust accretion around a central black hole, or all of these together. The challenge is to separate starlight from the furnace of feeding. An early black hole may hide inside its own beginning. This makes the young universe feel almost like a second kind of horizon, not a horizon that traps light forever, but a horizon of time, distance, and faintness. We look back as far as instruments allow, and the first galaxies appear not as comfortable spiral forms, but as small, irregular, redshifted sources still struggling to become themselves. Their light is ancient, stretched, and difficult to interpret. Every measurement carries both promise and caution. Inside those faint signals, a growing black hole may be only one ingredient among many. A young galaxy can be noisy in every sense. Stars form in bursts. Gas clouds collide and collapse. Supernovae explode and stir the environment. Dust absorbs and re-emits light. Radiation from massive stars changes the chemistry of surrounding gas. If a black hole is feeding at the center, its accretion light may blend with the galaxy's starlight, making the whole system difficult to separate into clean parts. This is why Webb's discoveries are so exciting and so demanding. It is not enough to find a red point of light and declare it a giant black hole. Astronomers must examine spectra emission lines, brightness, compactness, variability, and models of stellar populations. They must ask whether the light comes mostly from stars, from accretion, from dust, or from some combination. The early universe does not label its sources for us. It gives a signal, and science must patiently untangle it. That patience echoes the rest of the documentary. Sagittarius, a star, was not revealed by one glance. M87 star was not captured by one telescope. The event horizon was not understood by one metaphor. The singularity was not solved by naming it. The information paradox was not settled by one beautiful idea. Again and again, black holes require a slow movement from clue to interpretation. The early universe is no different. A faint galaxy may contain an overgrown black hole, or it may contain an unusual population of stars, or it may contain both. A compact red source may be a sign of accretion, or dust, or extreme stellar density. Each possibility changes the story of how the first black holes grew. Each must be tested against more data. The mystery is therefore not only that early black holes exist, it is that they force us to rebuild the childhood of galaxies. If black holes grew first, they may have shaped their galaxies from the beginning. If galaxies grew first, then black holes may have fed on the dense central gas created by early star formation. If both grew together unevenly, then cosmic dawn was not a simple sequence, but a tangled process of light collapse, feedback, and gravity. That tangled process is exactly what makes the final section important. Black holes are often treated as endings, the dead core of a star, the last destination of falling matter, the far future of gravitational collapse. But the early supermassive black holes remind us that darkness may have been present near the beginning of structure. It may have influenced how galaxies formed, how gas cooled, how stars were regulated, and how the universe became luminous. The dark centers were not waiting at the end of the story. Some may have helped write the first chapters. This connects the final section back to the first. At the center of the Milky Way, we found an invisible weight by watching stars move. At the edge of the observable past, we infer young black holes from faint spectra, compact light, energetic signatures, and the relationship between a galaxy and its central engine. Again, the unseen object bends the story around it. But now the scale has changed. We are not asking only what happens behind one horizon. We are asking when horizons first entered cosmic history. Did the earliest black holes form from the deaths of the first stars? From direct collapse, from mergers, from dense stellar clusters, from processes we have not yet fully understood? Which came first in some galaxies, the stellar city or the dark engine? The answer may not be a single path. The universe often makes similar objects through different routes. Some black holes may have begun as light seeds and grown quickly. Some may have begun as heavy seeds. Some may have merged. Some may have failed to grow. Some may have wandered in small galaxies before sinking toward the center. The population we see today may be the surviving mixture of many beginnings. This variety makes the mystery richer. A black hole may look simple from far away, but its origin may be complex. The early supermassive black hole problem also touches the evolution of galaxies. A feeding black hole releases energy into its surroundings. Radiation winds and jets can heat or expel gas. This feedback can regulate star formation, influence the host galaxy, and connect the black hole's growth with the galaxy's growth. In the modern universe, there are relationships between central black holes and the properties of their host galaxies. But in the early universe, those relationships may not yet have settled. Some young systems may contain black holes that seem large compared with their galaxies. Others may show rapid star formation with a buried active nucleus. The calm picture of a galaxy slowly growing around a central black hole may not fit the chaos of cosmic dawn. In the beginning, the city and the engine may have grown unevenly. Each shaped the other before either reached maturity. This gives the final mystery a different rhythm from the earlier ones. The singularity was hidden inside. The information paradox gathered at the horizon. The mystery of early supermassive black holes is spread across cosmic time, written in ancient light-distant spectra, compact sources, and the first galaxies. To study it is to look backward, not inward. And yet the feeling is related. Every early black hole marks a boundary that formed in a young universe. Every horizon was a region from which light could not return, appearing at a time when the cosmos itself was beginning to fill with light. The first stars opened luminous windows. The first black holes created regions of permanent silence. Cosmic dawn was not only the birth of light, it may also have been the birth of deep darkness. This thought widens the whole journey. Black holes are not rare mistakes in reality. They appear across scales and times. Stellar mass black holes can form from collapsing stars. Supermassive black holes anchor galaxies. Merging black holes send gravitational waves across space-time. Ancient black holes challenge the timeline of cosmic growth. The same basic idea returns in many forms: a horizon, a boundary, a region from which no ordinary signal comes back. And still, the deepest interior remains hidden. We can weigh black holes. We can image their shadows. We can listen to their mergers. We can infer their feeding in the young universe. We can calculate their entropy and radiation. We can ask whether their horizons encode information. We can compare their growth with the growth of galaxies. But no observation has yet brought a message from beyond an event horizon. That is not defeat. It is the shape of the mystery. A lesser story would pretend that black holes are now understood. A louder story would turn them into monsters or portals. The more honest story is calmer and more powerful. Black holes are among the best evidenced objects in modern astrophysics, and among the least accessible in their deepest nature. They are real enough to photograph by their shadows, strong enough to shake space-time, and mysterious enough to expose unfinished physics. They stand at the meeting point of knowledge and limit. At the center of a galaxy, a black hole gathers stars into orbit. At the edge of telescope power, it casts a shadow. At the boundary of relativity, it creates a horizon. In its interior, classical equations point towards silence. In quantum theory, it becomes warm. In information theory, it asks whether the universe can forget. In the young cosmos, it appears early enough to trouble our timelines. Each layer reveals another. Perhaps that is one of the quiet lessons black holes offer. The universe does not reveal itself all at once. Sometimes it gives us a ring of light and keeps the center dark. Sometimes it gives a mathematical boundary and hides the physical meaning. Sometimes it shows ancient galaxies and leaves us to ask how their central darkness grew. Science moves by approaching these boundaries patiently. It maps the stars around them. It measures shadows. It listens to space-time after horizons merge. It follows infrared light back toward the first galaxies. It admits where evidence ends and speculation begins. That patience is part of the wonder. As this final section comes to rest, imagine two scales at once. Nearby in the Milky Way, stars continue their long orbits around Sagittarius. A star. Far away in ancient light, Webb searches for growing black holes in young galaxies. Between them lies the history of cosmic structure. Stars born and dying galaxies, forming and merging horizons, appearing, feeding, colliding, and waiting. Some black holes are quiet. Some blaze through the matter around them. Some are remnants of dead stars. Some are giants in galactic centers. Some may have formed when the universe was so young that their very existence still troubles our simplest stories. And inside every one of them, the same silence remains. Not an empty silence, but a silence full of questions. What happens to matter after the horizon? What replaces the singularity? Where is information stored? How did the first giants grow? Do black holes mark the edge of what we can observe, or the beginning of a deeper theory of reality? We do not yet know, but we have learned how to stand near the darkness without turning away. By the end of this journey, black holes feel less like simple cosmic objects and more like boundaries where the universe asks its hardest questions. They began for us as invisible weights revealed by stars circling an unseen center. Then they became shadows, dark shapes outlined by glowing matter. They became horizons, causal boundaries no signal can cross outward. They became interiors where classical equations point toward a silence they cannot fully explain. And then they became stranger still. A black hole can have entropy. It can have temperature. It may radiate faintly across timescales longer than the life of stars. It may challenge the rule that information is never truly destroyed. Its horizon may not only hide the interior, but hint at a deeper connection between gravity, quantum theory, and memory. What makes black holes so powerful is not only what they conceal, it is what they forced us to understand more carefully. Around them, science has learned to measure the invisible through motion, to see absence through shadow, to hear collisions through space-time, and to follow ancient infrared light toward the first galaxies. Each step brings knowledge. Each step also reveals a sharper limit. That limit does not make the search smaller. It gives the search its shape. A mystery with no evidence is only darkness, but a mystery surrounded by evidence becomes something science can approach. Black holes are surrounded by evidence. Stars in orbit, rings of light, gravitational waves, accretion disks, ancient quasars, theoretical equations, and unresolved paradoxes that refuse to disappear. They are hidden but not silent. Their silence has structure. It bends stars. It curves light. It warms through quantum theory. It challenges the memory of the universe. It appears in the first galaxies and waits at the centers of the old ones. Every path toward a black hole brings us to a boundary, and every boundary teaches us something about the laws that brought us there. Perhaps that is why these objects feel so calm and so unsettling at the same time. They do not answer in a human voice. They do not explain what they keep. They simply remain while the rest of the universe moves around them, glows around them, trembles around them, and slowly gives us enough evidence to keep asking better questions. Perhaps that is the quiet beauty of this mystery. Science does not need every door to open at once. Sometimes it is enough to stand before the boundary measure, its shadow listen to the space around it, and admit that what lies beyond may require a deeper physics than we have yet found. If this journey helped you drift a little farther into the quiet of the universe, thank you for staying with me tonight. Subscribe for more calm science documentaries and tell me what mystery you would like to explore next as we keep listening together to the dark.